To approach this question, you have to read the criteria carefully. And one thing that we know after reading the description is that we're told that some factory workers speak all 3 languages, but not told how many. So we start with X in the middle then, because this is where they speak all 3 languages. Then we have 5 speak English and French, but not Spanish. So English and French, but not Spanish goes here. And then 1 worker does not speak French, English, or Spanish. So that means that he or she doesn't belong to all 3 circles. 10 speak English, Spanish, but not French. So English, Spanish, but not French is 10. And then no one who does not speak English speaks French and Spanish. So that means no one goes here. In order to figure out what goes in the bigger regions, we can start with the 65 who speak English, but that also includes the 10, the 5, and X, right? So that means this is 65 minus 15 minus X, giving me 50 minus X in here. 27 speaks Spanish, so this minus 10 minus X, so this is 17 minus X. And then French is 32 minus 5, so that means 27 minus X goes here. In number 2, find who speak all 3 languages. So all you have to do is add the subregions together. And that must equal to the entire factory's population. I have 109 minus 2x equals to 99, meaning that 5 workers speak all 3 languages. Okay. Number 3, find the numbers given in the diagram. So here, P of F and S and E. So this is intersection, meaning that someone who speaks all 3 languages, which is 5 out of 100, and 1 over 20. Okay. Someone who doesn't speak French at all. So this is 1 minus the probability of speaking French. So, or you can add up, the regions as well. So I have 5, 5, 27 minus 5. You can do it that way as well. And I believe that's 17 out of 25 when you simplify. And then E or F. So in this case, what we're looking for is anything that is contained inside the circles of E and F. So what do we have here? I have 50 minus 5, so 45 plus 5 plus 27 minus 5, which is 22. And then plus 10 plus 5 plus 0. So this is everybody found in those circles. That adds up to 87 over 100. And then what do we have here? We have P of E or F prime. So anywhere not in F or E. So this is 1 minus everybody who speaks French. Okay. And then we also include the region though for people who do speak English, because remember, or means more forgiving. So 27 minus 5 over 100. Okay, so 39 out of 50. Okie doke. Number 4. I'm going to show the shading in each Venn diagram as we walk through the proof here. So part A, E and U. So the universe is everything, and we're doing an OR. So that means we really have to shade in everything inside the universe. C, F and null. So and means anything in common. Well, of course, there's nothing in common between anything found in F and the null set that contains nothing. So that means the null set is null set, so nothing gets shaded in. Probability of E or E prime. The probability of E is this circle over here. Probability of E prime is anything outside of the circle. We're doing an OR, so that means we also include that, which means that we have shaded in the entire universe. G, P of U, well, of course, P of U is everybody, so it's equals to 1. On the right side, P of F and U. Now, it's something that is in common. Okay, so between the universe, which is the whole box, and common, which is the French. So I think French is over here. So only that piece, the circle, is shaded in, which is P of F. D, P of S, union with no. So P of Spanish or the no set. So that means or is the forgiving one, right? So this is S, so P of S is like that. F, P of E and E prime. Now this is different from E or E prime, and is anything common. So if I talk about an event and anything that doesn't belong to the event, nothing is in common, okay? So number 5, how do the results from 3C relate to the individual probabilities of P of E and P of F? So 3C told us that E or F is to include everything in E and anything else in F. But if I do include the entire F, this middle region got counted twice, correct? So that means after I add E and F together, I need to subtract that middle region, which is the end. Okay, in order to say that this is P of E or F. So that means we have to subtract that middle region, okay, as an answer to number 6. So now let's recap what we have learned about OR events from the investigation. So we said that the OR event or the union of two events, P of A or B, is given by P of A plus P of B minus P of A and B, okay? And for two mutually exclusive events, so you can think of disjoint sets when you represent that on the Venn diagram. You can recognize that you should know that the intersection of the two events does not, you would know that the intersection of the two events is a null set. It's nothing. So the value of P of A and B would be 0 anyway. So we can simplify your formula into P of A or B equals to P of A plus P of B. In the event of 3 events, you can use this formula. So you're going to add P of A, P of B, P of C. We know that we're double counting right away, right? We're double counting all the common regions between any two events. So you subtract P of A and B, subtract P of A and C, subtract P of B and C. But then when you do that, you will actually be taking out the middle section too many times. So you have to add it back at the end. So plus A and B and C. If you don't trust me, try to prove it for yourself using a Venn diagram, okay? So we do mention here we did mention the term mutually exclusive. So we mentioned the term mutually exclusive. So in example 2, let's try to identify which set of events are mutually exclusive. Event A, you're randomly drawing a gray sock from a drawer. You're randomly drawing a wool sock from a drawer. So the question to ask is, can you have socks that are gray and made out of wool? The answer is yes, right? So that means these two things can be in common. A and B can be common. So these are not mutually exclusive. How about B? Event C, your birthday falling on a Monday next year. Event D, your birthday falling on a weekend next year. What about that? Well, Monday's not in the weekend, right? So yes, these are mutually exclusive events. Example 3, we're going to use a tool that is commonly found in probability questions, which is a pair of dice. So you toss a pair of dice, you want to know, well, what's the probability of rolling pair? One useful tool that you'll be relying on is the dice table. So this dice table shows in red, okay, the column and row headings are the possible up faces that you get from die 1 and die 2. And then in blue, in the field, it is the combination, right? It's the sum of the two dice. So 1 plus 1 is 2, all the way to 6 plus 6 is 12. The way it shows is that out of the 36 possible outcomes, you're going to have increasingly, probability from getting a 2 to 7, and then it starts to decrease again from getting an 8 to 12. So using this chart, what is the probability of rolling a pair? Here we have a pair is 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So there are obviously 6 possible outcomes out of 36. Okay. And then P, finding a sum of 6. How many 6s do we see here? We see all the 6s across this short diagonal. So there are 5 events. So here, 5 out of 36. Now, the bigger question here is, what is the probability of rolling a pair or a sum of 6? Does it sound familiar? It should, because this I can consider as the probability of rolling a pair plus probability of getting a sum of 6. But then the double counting tells me that I need to subtract the probability of getting a pair and a sum of 6. So 6 over 36 plus 5 out of 36 from parts A and B. What is the probability of getting a pair and a 6? So here on the chart, I can tell that amongst all the 6s, one of them is a 3 and 3. So this is a pair, which means that we should subtract this probability, okay, from the total. This gives me 10 out of 36 or 5 out of 18. Okay. Last question. So here we're talking about a standard deck of cards. So a card is randomly selected from a standard deck of cards. When we say that, that means that we are not including jokers. Okay. How many cards are there in a standard deck? Think. You have a 2, 3, all the way to 10, and then Jack, Queen, King. And then, out of all these cards, how many times do they repeat? We have 4 suits, right? Hearts and diamonds, okay? So 4 suits. So our question here is, what is the probability that either a spade or a face card is selected? If you want to avoid writing spade and face repeatedly, what we can do is we can say let A be the event of picking or drawing a spade, and then let B be the event of drawing or picking a face card. Okay, so now the either or tells me that I'm curious to look at P of A or B, which is P of A plus P of B minus P of A and B. Okay. All right, so let's think. What is the probability of drawing a spade? There are from A to K, well, A to 10 and the Jack, Queen, King. So that's 13 spades. Out of a deck of 13 times 4, which is 52. Okay. Plus B, the event of picking a face card. So how many face cards are there? Jack, Queen, Kings. These are face cards. Again, there are 4 suits, so there are 12 face cards. There are 12 face cards in a deck out of 52. And then we need to subtract the common elements. So what's the common element here? We're talking about face cards of spades. Okay, so Jack of spade, Queen of spade, and King of spade. So that's 3 cards out of 52. So let's simplify this. 13 minus 3 is 10 plus 12 is 22. If I have that, it's 11 out of 26. Okay, so that's the probability of getting either a spade or a face card.